Crop diseases are one of the biggest threats to global food production. Every year, farmers lose billions of dollars due to infections that damage or destroy their crops. Many of these diseases go unnoticed until it's too late, impacting yields, farmer income, and even national food security. Now, imagine if we could detect these diseases early just by taking a picture with a phone. Thanks to artificial intelligence, that's no longer just an idea, it's a reality. With the help of deep learning and image recognition, we can now identify plant diseases quickly, accurately, and automatically. And that's exactly what our project is about, detecting and classifying plant diseases using AI and computer vision. In this video, we'll take you through the entire process of how we built this smart system, from collecting data all the way to deploying a real-time interface. Then, we'll show you how the code works in Google Colab, step by step. Let's first look at the workflow of our project. We begin with environment setup. We use Google Colab, which gives us the tools and GPU power needed to train deep learning models. First, we mount Google Drive to access our files and install the libraries we'll need, including RoboFlow, Ultralytics, and Gradio. Next comes data collection. We use a high-quality labeled dataset from RoboFlow that contains images of both healthy and diseased plant leaves. To make our model more robust, we apply augmentation techniques like rotation and brightness adjustments, increasing the variety of training data. After that, we move into data pre-processing. We resize and normalize the images so they're compatible with YOLOv8, which is the model we're using. Pre-processing ensures all the images are clean, consistent, and ready for training. Then comes the most important step, model training. We train YOLOv8 on our dataset. Over the course of 100 epochs, the model learns to recognize patterns and symptoms of plant diseases. It gets smarter with each batch of data, improving its ability to detect even subtle signs of infection. Once training is complete, we evaluate the model. We test it on unseen images to check its performance. We use tools like confusion matrices and accuracy graphs to understand how well it's doing. If needed, we make adjustments and retrain to fine-tune it further. Finally, we build a user interface using Gradio. This allows anyone to upload an image or even a video, and the system will analyze it and highlight any disease it finds. It's fast, accurate, and easy to use. And if you'd like to access the full code, datasets, and resources for this project, you can visit Aionlinecourse.com. There, you'll not only find this crop disease detection project, but also a wide range of AI and machine learning projects designed for students, researchers, and enthusiasts, just like this one. It's the perfect place to learn, build, and innovate with real-world AI applications. Now, let's jump into the actual code demo on Google Colab and see how everything we just talked about works in practice. First, mounting Google Drive. We mount our Google Drive so that we can easily access our datasets and also save any outputs or model weights during training. Next, installing required libraries. We install RoboFlow to pull in the dataset, Ultralytics to use YOLOv8, and Gradio to build our final interface. Connecting to RoboFlow here, we use an API key to connect to our RoboFlow account. We then load our specific plant disease detection project and download the dataset formatted for YOLOv8. Importing libraries, we bring in all the tools we'll need, like PIL for images, OpenCV for video processing, Matplotlib for visualization, and NumberPy for array operations. Of course, we also import YOLO from Ultralytics to handle the model. Training the model. Now, we start training. We use the lightweight version, YOLOv8 and .pt, and train it using our dataset for 5 to 100 epochs. The model begins learning how to spot disease areas in the images. Viewing confusion matrix. This line opens and displays the confusion matrix generated after training. The confusion matrix shows how well our model has classified each disease class, helping us understand which classes it's confusing the most. Viewing training results. This command shows us the training results summary image. It includes graphs for precision, recall, and loss curves. This helps us visually understand how well the model is learning over time. Viewing training samples. Here we open an image that shows a batch of images used during training. It includes bounding boxes and labels to confirm the model is learning from correctly labeled data. Validating the trained model. Now, we validate the trained model using our validation dataset. The model calculates important metrics like MAP, mean average precision, at different confidence thresholds. These scores help evaluate how accurate the model is. Viewing validation confusion matrix. This opens the confusion matrix for the validation data. It helps us see if the model is overfitting or generalizing well to unseen images. Visualizing validation batch. This displays a sample batch from the validation set, along with the labels. Again, it's useful for confirming that the model is correctly interpreting unseen data. Loading the trained model for prediction. Here, we load the trained model by specifying the path to the best weights file from our training run. This model is now ready to make predictions on new images. Running a prediction on a test image. This line uses the model to predict diseases on a test image. It sets the confidence display off and saves the resulting image with predictions. The detected disease areas will be highlighted with bounding boxes and labels. Image prediction function. This is a custom function to predict plant diseases from one or multiple uploaded images. It reads each image, runs detection, adds bounding boxes and labels, and then converts the result back into an image format that can be shown to the user. Video prediction function. This function is designed to detect diseases in videos. It reads the video frame by frame, applies the trained YOLO model to each frame, draws bounding boxes, and saves the processed video. This way, we can detect diseases in real time or pre-recorded field videos. Processing both images and video. This combined function calls both the image and video prediction functions. It's used as the main processing unit in our interface, handling whatever the user uploads, whether it's photos or a video, creating and launching the interface. Finally, we use Gradio to build a simple interface. The user can upload multiple images or a video, and the model will return the processed results. The interface has 3 output panels, one for images, one to show the input video, and one for the processed video. Then we launch the app to start using it. Here I have uploaded a fresh peach leaf, and it perfectly recognized the leaf, and it hasn't detected any disease. That's it. From collecting the data to training the model and building the interface, you've now seen the full process of how we built a smart crop disease detection system using AI. Thanks for watching.